Hey, AP physicists. Today we want to talk about potential energy functions, and that's the area that we're going to deal with calculus. So whenever we look at potential energy functions, remember that the derivative is nothing more than a slope, and the area is nothing more than, I just said it, the integral is nothing more than the area. So the integrals are areas. So whenever we look at this force equation, work is force times displacement, which remember then will be converted into potential energy. If I'm looking at a force displacement graph, let's just say that it has a constant force acting on the object for a certain distance, then you can very easily see that that area, the force times displacement, is going to be the energy expended or the work done on the object. So more generally then, let's say that we don't have a graph where this is a constant force. More generally, we would look at that as the integral of the force with respect to the position. That's going to give us the work done or the energy involved. If I rearrange that so that I'm looking at the potential energy, then I can say that the potential energy is the negative integral of the force with respect to the position. The force is the force that is exerted by the spring or the gravity, or it's the restoring force. So you have to kind of get out of the mental mindset. This is not the force that you're putting on the system. It's the force that the system is putting on itself to get itself back to its normal position or its equilibrium. Because that's the opposite frame of reference, that's why we include the negative there. So it's not your frame of reference, it's the frame of reference of the system. The negative you can also think through whenever we talk about energy. So energy is a scalar value. Remember that with vectors, that energy tells you the direction that is the object is going to go. But whenever we talk about a scalar value, the positive negative tells you whether you're gaining or losing energy, which you could think of as kind of like a direction also, but it's not a direction in terms of what you're thinking, like north, south, east, west, or positive x, negative y, those kind of things. We can rearrange this equation then, the potential energy function, to solve for a force. And then couldn't we also look at a graph that maybe this is a potential energy versus position graph and say that, hey, if I have a potential energy that's increasing like that, then the slope of that line is going to be the force that's acting on it. So it's going to be the negative change in potential over the change in position. Okay, so that gives you sort of a general idea of where that goes. Now, how would we apply that? So a spring follows a force equation of F equals 52.8x plus 38.4x squared. So how much work is done from x equals 0.5 to x equals 1 by u? What we're going to do then is we're going to take and say, well, hey, that work is the integral of the force function. So I'm going to put the force function into that integral. Remember that this is a definite integral. I have a from a half a meter to 1 meter. And then whenever we do that, I took away the negative only because this is the force done by u, not the force done by the system. So when I integrate it, remember I'm going to raise this power by 1 and then divide the coefficient by the new power. I'm going to raise this power by 1, divide the coefficient by the new power, and then take this from 0.5 to 1. So if I put this in as 1, I didn't do that here, sort of the intermediate step. This whole function with the 1 inside of it's going to go into here. The whole function with the half inside of it's going to go in here, and then we're going to subtract the 2, and that's where we end up with a work of 31 joules. Is how much energy you would put on it. Now, how much energy would it take for the spring to restore itself? It would take negative 31 joules because it's going to take that energy and pull itself back together. So the next step to that is going to be a conservation of energy problem where we say, hey, a mass is placed on this spring horizontally. So maybe this is a spring that's like this. So maybe if I draw this slightly different here, maybe it's a coil here. And it's normally like that, but what we're going to do is we're going to compress the coil so that now the coil is pushed together and there's a mass pushed on it. And what the spring wants to do is it wants to extend itself back to equilibrium. So what we can do from that then is, I wrote right over where my work is going to be, work is going to equal the kinetic energy. So that 31 joules has to equal 1/2 mv squared, the amount of energy that's put into the mass as it's being released. And so when we plug in the mass, we can solve for how fast it's going. Now, what this didn't say was it didn't say anything about friction. So because it didn't say it, I assumed that there was no friction. Oftentimes it will say that the mass is placed on a smooth surface. So the word smooth is often equivalent to no friction. And if it does include friction, so let's just say that we included friction into this, then all that would happen is we would have another energy that's coming out here that's the work that friction does. And remember that that work is going to be the force of friction times the position. We can take that force of friction and say mu force normal times position, and we can say that that's the energy that's coming out due to friction. You will oftentimes see this also written maybe as the work of the spring minus the work of friction is equal to what we have left, kinetic energy. A lot of times people will do that because then we're left with this kinetic energy, and we could say, well, maybe that becomes some other kind of energy on the outside of that. It doesn't really matter which way you look at it. Both of those are correct as long as you get to the answer that we're doing. Okay, so moving on then, whenever we look at unstable, stable, and neutral parts of a position, potential energy position. Let's say we have a potential energy function that looks something like this, like maybe a roller coaster, okay? Actually, I want to level it out on the end. So here, this, and then it comes over to a flat surface like this. There are certain points on this, and I'm just going to pick the highest point here. I'm going to pick the lowest point here, and I'm going to pick this flat surface here. Those are sort of my max, my min, and my balanced or flat part. Okay. For part A, it is considered to be unstable because the slope on either side of where A is pushes the object away from the position. So left to the left over here, this slope is positive, which means that whenever I put into that force function, so remember force is equal to the negative du dx. Du dx is the slope. So if I have a positive slope there, I'm going to put the positive value in there. That means I'm going to get a negative force, which means that the force is pushing A away from that position. If I look on the right side, the slope is negative. So when I put the negative in, I'll get a positive force. So anywhere over here, the force is going to push A to the right. And that's why that's an unstable position, because anywhere except right at that very top peaky part, it's going to want to push away from that part. You could think of this as like maybe this is a track and we place a marble there. If I put a marble there, is that marble going to stay there? Is it going to be stable, unstable, or neutral? It's going to be unstable because there's a great chance that the marble is going to slide off left or right. Now, the opposite works at part B. We have this is going to be a stable part. This is kind of a well here. So the slope on either side pushes it back towards the position. So the slope on the left here is negative, which means that when I put the negative in, I get a positive force pushing the object back towards the center of that well, or back towards the center of that hole there. If I'm on the right side, then the right slope is positive. Put in a positive slope, I get a negative force, which means that it's going to push it back that way. And that's why it's stable, because if I bump part B, that marble B, either left or right, as long as I don't get it higher than this line here, then the marble is just going to oscillate back and forth until it goes back into that divot or back into that bump. And that's what we would call an energy well, or a gravitational well if we're talking about gravity. I'll show you a picture of that here in a second. The last one is a neutral position, and that would be where a small displacement doesn't create forces. And so if you think like the slope here is 0, so the slope in this F equation would be 0. So if I do F equals negative 0, then I'm really going to have 0 force. So if I bump C to the left or the right, nothing really big is going to happen because there's no restoring force trying to push C one way or the other, and that's why it's considered neutral. So to go back to that energy well idea, here is a picture of our solar system's energy wells. XKCD has a whole bunch of scientific comics that are really, really, really cool. So if you get a chance, you're bored someday, Google XKCD comics, and you'll get a laugh out of any of the ones. Like pick your favorite science, Google XKCD science, that science, and then you'll see. So you can see here we have the different planets. There's Mercury, there's Venus, there's Earth, the moon is there, Mars. Jupiter, because Jupiter has such a big mass, it has a really big energy well. You can think like when we want to get away from the Earth's surface, we have to put enough potential energy in to overcome the Earth's pull towards that satellite. So to go to the moon, we have to overcome the Earth's pull to get to the moon's gravitational and go into that energy well. If we're going to Venus, it's not going to take as much energy because the sun is pulling us towards it, which will pull us towards Venus and pull us into Venus's energy well. If we want to go out of the solar system further out, notice that we're going to have to get more energy because, again, we're working against the energy well of the sun. And you can see here the sun is very, very, very far down because the sun is so much mass that it really takes up for most of the rest of that. Okay, so that's kind of gravitational wells or energy wells and the potential energy. Okay, so now that we talked about stable, unstable, and neutral, let's do a sample problem for that. An object follows a potential energy function of 3x cubed minus 7x. So what is the function of the force? We want to find what's the equation for our force, and then where is it stable, where is it unstable, and where is it neutral at? So to get the force, remember that the force function is going to be the negative derivative of the potential energy function. So I'll have the negative derivative of 3x cubed minus 7x, all with respect to the position or with respect to x. So taking that derivative, I would take 3 times 3 is going to be 9. X, drop the power to 2. So 1 times a negative 7 will be negative 7. To drop the power to 0. And then all of that is going to have the negative in front. So my force function is going to be negative 9x squared plus 7. So you'll notice that over on the right here, I put 2 different graphs for us to draw. The force function graph is going to help us draw the potential energy function graph. So when I look at my force function, I can find 2 different things. I'm going to know that my x-intercept is whenever I'm going to make my function equal to 0 and solve for x, minus negative 9x squared plus 7. And then solve for x, I'm going to get x squared is equal to negative 7 over negative 9. Get rid of my negative signs, so I can get rid of those. And then I'm going to square root that and get rid of my squared value in order to solve for x. So when I square root that, I get a plus or minus 0.8819 for that value, 0.8819. So I know that that is where the object is going to cross at the x-intercept here. So 0.8819 negative and positive 0.8819. Then I can look at the y-intercept. And for the y-intercept, I'm just going to set my x value equal to 0. And when I do that, I end up with a force of 7. So up here at the top of this, I'm going to have a 7. I know that it's going to curve this way. It's my parabolic function that's going to do that. I also know that whenever I go up to this cubic function for my position 1, these are going to be important. They are going to be my max and my min values. So I'm going to draw those up here also so that you can see those correlations on the graph. What I want to do then is I want to plug that 0.8819 into those. So I'm going to put in the positive 0.8819 cubed minus 7 times 0.8819. And then I'm going to also do the same thing for the negative value. And that's going to give me a 4.41 plus and minus value. So I know that when I put in the positive one, then I'm going to get a negative value, which means that down here I'm going to curve this way. And then when I put in the negative one, I get a positive value. Up here, I'm going to curve this way. So this is going to be at the negative 4.41. This up here is going to be at the positive 4.41. And then the last thing that I can do is find out that what is my y-intercept, where is my y0? And that's actually very easy because when I put in x as 0, then my potential energy function turns out to be 0. So I'm going to have a 0 value here. So looking at this function, I know that it's going to curve like this, come down like this, and come up like this. Now, that makes it fairly easy to solve for where is it stable, where is it unstable, and where is it neutral. When I want to find the stable parts, remember that's a part where if I move the object really slightly, it's going to go back to its original position. which means that if I can do this very quickly here, change my pen color, over here at this point here is where it's going to be stable. So I'm going to put a B there for the stable, because that's B over here. Then where is it going to be unstable? It's particularly going to be unstable up here. I'm going to put a C there because that's my C. Where is it unstable at? Although it is unstable at all those other points too, but it's the most unstable at that point. And then I want to talk about where is it neutral. Is there any place on here where if I bump it slightly, it's not going to really move much? And that is, the answer to that is nowhere, because there are no flat surfaces at that point where it's unstable. So we end up with a force function graph of this. We use that force function graph to find maxes and mins, the values of where the position is max and min, by setting it equal to 0 and then plugging that x value back into the position function and then solving for those to find where it is stable and unstable. So lastly, we're going to talk about other forms of oscillating energy, and this would be examples of where the energy is going back and forth from one energy to another, maybe potential to kinetic to potential to kinetic. And so whenever I look at this potential energy function, that function is usually going to be some form of a parabola that is going to do something like this, okay? So I'd have, if I put the object here, I'm going to have all potential energy at that point. As it comes down, all of that potential energy is going to convert into kinetic energy, which is going to roll back up to the other side at the same height with the exact same amount of potential energy on that side. Then I can look at anywhere in between, like maybe when the object is here, there is still a potential energy because the object has a height, but not all of it is potential energy. Some of that has converted into kinetic. And remember, when we look at that, we would say energy is energy is energy. This energy has to equal this energy, has to equal this energy, has to equal this energy. It's just constantly changing from one thing to another. So the reason this is oscillating then is because this marble or whatever this is rolling back and forth and changing potential to kinetic to potential to kinetic to potential. So an example of that might be if I'm looking at an oscillating spring, maybe this is the horizontal spring we were talking about earlier. So that I have a horizontal spring here, and then that horizontal spring is compressed. This is maybe a frictionless surface, and it will oscillate back and forth. So it will uncompress here, and then it will go back to here, and then it will go back to here again, and it's just oscillating back and forth there. So it'll be the potential energy of the spring that turns into kinetic energy, that turns back into potential of the energy of the stretched string, and you kind of get the sense there. When we're dealing with roller coasters, go back to this. So I might say that the potential energy of the spring has to equal the kinetic energy. So this would be 1/2 kx squared is going to equal 1/2 mv squared. Obviously, that becomes a little bit more complicated if we throw friction into there, where we would have energy that we're losing to friction. And that's what we would call dampening, where it's slowly losing energy and it will oscillate less and less and less and less until it ends up back in that equilibrium position. Now, if I'm dealing with a roller coaster, maybe I have a coaster that does something that looks like this. So I have the first hill with the first big drop, and it comes down, and then it oscillates back up here to become potential and kinetic. We know there's a little bit of kinetic there because of the value that the height hasn't gone back to the original height. So to begin with, I could say this potential energy has to equal this kinetic energy, and I can do potential is equal to kinetic, where I have mgh is equal to 1/2 mv squared. Now, at the second hill, I might say that that's equal to mgh, the second height, so I'm going to put a 2 there, plus 1/2 mv squared, a second velocity, which will be the velocity at the top of the second hill. And again, remember, energy is energy is energy is energy. Now, a pendulum, example of that might be if I have a string here and I put an object hanging at the end of the string and then I let it swing back and forth. This could be a swing set at the fairgrounds. You go out, it's going to have potential at the top here. All that potential turns into kinetic at the bottom, which turns back into potential again at the top. So you can see the oscillation that's happening there. And again, that's going to look very similar to the roller coaster, where I have the potential becomes the kinetic. Mass times gravity times height is going to equal 1/2 mv squared. And I can solve for the problem based on whatever it's asking for at that point. So I hope that gives you an idea of the different kinds of potential energy functions that we would look at, how the calculus ties into this unit, and then how to do some of those problems.